Water pressure acts blank to surfaces of an object. So this was about directions. You had options of parallel, perpendicular, all or none. So when water puts pressure on something, or to make it something that we can see right now, when air is putting pressure on me, what direction is the force that the air pressure is putting on my forehead? It's going into the surface. The force applied by a fluid is always directly into the surface it's contacting. So that would be perpendicular.
1 out of 4.
Which property is proportional to the squared speed of the molecules? Now this one was a little bit tricky probably, just because, it's got the squared speed in there. But let's just look at these one by one. What is density? The mass over volume. Does mass depend on the speed? No. It just depends on how many molecules you have. What about volume? Okay, if you have a solid, we learned that there is a small amount of expansion that occurs when we heat it usually. If you have a gas, it expands more, but with the gas, you can also just put more pressure and compress it. So as Brandon said, no, there's not a direct relation between volume and temperature either. Now, if you keep it at constant pressure and it's a gas, there will be, but not as a general rule. So we've ruled out volume and we ruled out density. Pressure. Pressure is the force per area for the molecules hitting a surface. And if the molecules are moving faster, they're going to transfer more momentum when they hit the surface, and they're going to hit more often. But the pressure can also be changed by putting more molecules in and not changing the speeds. So it's not that simple. That leaves temperature. If you're in a gas, we have, and I didn't show you the equation, I just talked about it, but the equation is that the average kinetic energy is equal to 3/2 a constant multiplied by the temperature. And since kinetic energy is 1/2 mass times, actually it's V squared average. Got them in the wrong order. Then the temperature is telling us about that average of the squared speed. And so the correct answer there was temperature. Okay, number 3. And if you have questions, just make sure let them be known. Number 3, the weight of water displaced by an object is equal to, and this is Archimedes' principle. I read the book's little inserts on Archimedes' principle last night, just to review. And I guess it was King Hieros, or how do you pronounce it, Hieros II, that the story is about. But remember his principle, what we studied in lab this past Thursday, was that the weight of the fluid displaced is equal to the buoyant force, how much is being pushed up on the object. So the correct answer is the buoyant force acting on the object. Why is the net force not correct? Because does work with like a 5-year-old? Because I said so works even with a 6-year-old?
Well, I was going to keep going.
Oh, okay.
But does that have anything to do with something you can float or no?
Well, when we have an object that's in water, whether it's sinking or floating, it's going to have two forces. The buoyant force pushing up and the force of gravity pushing down. And together, those are going to make the net force. Now, we could have other things like if it's sitting on the bottom, there'd be a force normal. If it's hanging from a string, there's a force of tension. But you have at least those two forces. So the net force is not the same as the buoyant force. The buoyant force is always going to be just equal to the weight of the displaced fluid, where the net force is looking at all the forces acting on it. And of course, the density is not a force, so that couldn't be the right answer. And finally, the weight of the object. The weight of the object would be true if it is floating, because if it's floating, the buoyant force is equal to the weight. It's in equilibrium. So this one would only be true if floating, but it didn't say it was floating. And I mean, I went with the answers the student gave. I didn't try to be tricky. Last one. A calorie is defined as the amount of heat. I know this is Brandon's. Is the amount of heat necessary to raise how much water by, well, what unit of water by what unit of temperature. So
our potential test questions.
Quiz questions are always exclusively your potential test questions. Yeah.
Wow. I guess can we get those? Or you get them online?
Yes, although I got them graded last night and they're scanned, but I haven't got them returned. But yes, you get them back, and about half the test questions will also be from your potential test questions.
That's great.
So, and remember, I even told you if you've got a little red scribble in the corner, that means it went into the database from which they'll be chosen for quizzes and exams. So when you get them back, when you see those, that's telling you this one was selected to potentially show up. Doesn't mean it will, but potentially will. Okay, so what was it, Brandon?
I think it was C.
Way to be confident. You're right. A calorie is defined as the amount of heat necessary to raise 1 gram of water 1 degree Celsius. And in fact, it's really more precise. It's the amount of heat required to raise 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius. But for class at this level, we're happy to say, well, that is 1 degree Celsius, and it's pretty similar as you change temperatures. But I think it's because it does change just a little as you change temperature. That's why you have different numbers, to relate a joule with a calorie. Something that I actually let it select 6 questions, and then I struck 2 of them. One of them was the relationship between a dietary calorie and a physics calorie. What's the relationship between those two? A dietary calorie is 1,000 of our physics calories. All right. We did the demonstration of this last class period, bending this metal strip. Now, this metal strip is really 2 different strips made of different materials. And because materials expand when you heat them and contract when you cool them, for most materials, not for all, but for most, because they expand when you heat them, this gets longer when I heat it. And you saw my example with these of the ball getting larger when I heated it. And the ring also, the hole in the ring got larger when I heated it. But this, because it has 2 different kinds of metals, the different metals expand different amounts when you change the temperature. And so one side expands more than the other, and that makes it curve. So this can be used as a temperature gauge. You can take this and you can measure how much it curls, and knowing what the 2 materials are, you can calculate what temperature results in that much curl. Or you know what you do in practice? You probably just calibrate it. You probably just say, okay, I heat it to this temperature and it's curled this much, heat it to this temperature, it's curled this much. So I don't know about you, but when I grew up, my mom had a garden thermometer or thermometer out there to tell her what the temperature was in the garden. And of course, I had to see what it was. And so when you take it apart, you just have this big coil of wire and then an indicator sticking off of it. And I was like, well, that's the silliest thing. I have no idea how that works. It's some kind of spring is what I thought. But now that I study physics, I'm no longer a 7-year-old child, I know that this is a bimetallic strip. And if the temperature increases a little, it's going to curve a little more, and it's going to move that needle. And the amount it moves the needle will be depending on how much the temperature changes. And so it's calibrated so that needle is going to tell you what the temperature is as the lengths of the 2 change. So that's an example of a bimetallic strip in a very practical way. A standard thermometer, the kind you stick under your tongue. A standard thermometer works by looking at how much the volume changes of a material when you heat it up, a fluid. Back as a child, we used mercury thermometers. Now they use almost exclusively alcohol. And so you have that alcohol in there. As it heats up, it expands. And then you measure how much it expanded to determine the temperature. So that's how our two most common types of thermometers work. There are some other types. There's something called a thermocouple that's looking at chemical changes. You have what's called the Fermi energy, the energy of the last electron in your metal, and that also changes with temperature, and that's what a bimetallic strip does. So if you've ever seen a probe that is just wires twisted together that's measuring temperature, that's what it's doing. You actually develop a voltage difference because of that change in the Fermi level. Here is something that you're probably familiar with since we live out here in Nebraska. Water is not normal. Water does something exactly opposite of almost everything else. Water, when it freezes, well, what does it do when it freezes? It expands. And that expansion causes us big headaches. It causes, if you didn't blow the water out of your sprinkler system, that those pipes that are underwater, if it got cold enough for the water to freeze in there, the water could freeze, expand, and now be too big to fit the pipe and break your pipe. How many people have experienced this fun? Wow, just 3. Congratulations to the rest of you. I did say, didn't I? Congratulations, Renee. All right, Renee. That's your middle name, isn't it, Brittany?
Yeah.
I gave you grief before, so I have to, give you congratulations. I only watched the first half and I liked it, and then we had worship and went to bed.
Oh, gee,
Oops.
that's what happens when people call us away.
That's right. So what happens to make ice do this crazy thing? Ice is a different kind of solid than most solids. It forms, it's what we call a Van der Waals solid, and it forms a funny kind of bond when we study chemistry, which is coming up in 2 weeks?
Yeah. Thank you. I love chemistry.
We'll learn about different kinds of bonds, and this is a funny kind called a Van der Waals bond, and that bond actually makes it so it spreads the molecules out when they form a crystal. In most cases, when you form a crystal, it's like this. They fall into a nice, neat packing order where they take up a minimum amount of space. But the water crystals don't do that, and because of that, they take up more space and expand. So I talked about a negative thing about it. It's not purely negative. It's not, 4 degrees is when water is most dense.
Most dense at 4 degrees Celsius.
It's most dense at 4 degrees Celsius.
Is there a particular reason? Just that.
It has to do with starting to form those Van der Waals, starting to get the organization.
Okay.
So here's a graph that shows you going from 0 to 18 degrees Celsius. What's 18 degrees Celsius in Fahrenheit? Ballpark. I'm not asking for somebody to actually calculate, just ballpark. Okay, if it was 20 is 68. So it's going to be, just a little below that, go down approximately 2 Celsius for, 2 Fahrenheit for every 1 Celsius. It's 9/5 is the actual ratio. So it's about 4 degrees less than 68, about 64. So somewhere in that ballpark, down to 0 Celsius. What is 0 Celsius in Fahrenheit? 32. That's one you should know. So it's most dense there, and this graph here gives you the full details. You see that it's not a straight line. It doesn't increase linearly with temperature, but we generally approximate, for all materials, a linearity. So we approximate that that's a straight line. It wasn't, right? But that's what we approximate because it's close. And you see ice here. I've got to get rid of that tool. Sorry. The ice is a much higher volume, which means a lower density. Well, I said much. That's about 8% higher volume. But 8% higher volume is enough to break your pipes. And you see, this here means that it actually is way up there. It's a big shift. That's what that little jag means. Otherwise, you try to read this and say, wow, who would have guessed water vapor is only slightly bigger volume? It's way, way bigger volume. So now let's look at positives of this. One positive of the fact that ice expands when it freezes is that ice floats. Because if it expands when it freezes, you have the same mass but more volume, it's less dense. And less dense things float on more dense things. So ice floats. If it was not so, we would have an ice cube. Because in the winter, you would form ice crystals on the top of your lakes and they'd sink to the bottom. And you'd form more ice crystals on the top and they'd sink to the bottom until you fill the lake up with ice. But because the ice floats, you form ice in the top and it forms an insulating barrier. It makes it so heat can't flow out of the water as quickly, and so it keeps you from freezing the water underneath. And that means that we can have a happy fish down there swimming in the lake that's frozen over the top until some Norseman comes and drills a hole and dingles his.
It's actually warmer down there than it is like above the ice.
Yeah, because the earth is warm.
Okay.
And so you have heat coming out of the earth, and then
It's trapped in the ice.
Yeah, it can't get out quickly through the ice. And also, because it has the lowest density, it's going to move toward 4 degrees just because of the pressure. Or not lowest, the highest density. It's going to move toward that. So, we don't have our lakes freeze solid. The fish can live through it. Now, there are some fish that actually can be frozen and thawed, which is a miracle.
And survive.
Yeah, and survive.
You know that
Well, yes.
you buy them at the grocery store.
Yes, you buy them at the grocery store, but you can't revive most of the fish you buy at the grocery store that have been frozen. But there are some that can. But most fish would die. And so that allows them to live, and it allows our earth to remain warmer than it would otherwise. Just things I just said. We're going to talk also today's lecture, hopefully we'll get there, about the greenhouse effect, which is very important. If we don't have the greenhouse effect, once again, we're just icicles. There'd be no life on Earth without the greenhouse effect. But of course, if the greenhouse effect is too bad, then we get too hot. Yeah. So now we're starting chapter 6. We are 2 lectures delayed. I know. I'm sorry about that. So talking about heat, let's back up just a step. What is heat? Transfer of thermal energy. Remember I said a lot of people get confused and think that heat is energy. But heat is a transfer of energy. And heat specifically is a transfer of energy without doing work. Work is a force making something move. But heat is just a transfer of energy because this thing's hotter than that thing. Higher temperature, lower temperature. The second law of thermodynamics says heat naturally flows from hotter to colder, not from colder to hotter. Which brings up some questions that hopefully I'll have time to answer about how we can make a refrigerator that will make it colder in the cold area. So there are 3 processes by which we can have heat transfer. Number 1 is conduction. I am not going to light my fire yet because conduction, well, I'll just burn myself. But imagine that this Bunsen burner, actually, it's probably not a Bunsen burner, it's probably somebody else's design, that this burner is running and I touch it with my finger. Yeah, what's going to happen? My finger's going to burn. Why is it going to burn? Because energy will flow into my finger really quickly. And that energy is then going to raise the temperature of my finger to an unsustainable level. So that's conduction. Conduction is a transfer of heat due to direct contact. And, well, I have slides for each one of these, so I guess I won't go to the next one until I show you the conduction. You guys have probably experienced, today there's this fad to put hardwood floors in your kitchen or in your house, right? And so you get out of bed and you put your foot on the carpet. And what does that carpet feel like in the morning? It feels good, right? It doesn't feel cold, it's comfortable, soft. I love carpet. I carpeted my whole house except for the kitchen and bathrooms because I prefer that to hardwood floors. But if you get out of the bed and you put your foot down on a hardwood floor, what does that feel like? Cold.
That's tiles.
Asbestos tiles.
Or dirt.
What's the difference? You laugh.
There's
energy being transferred.
More energy can be transferred to the hardwood floor than the carpet. And most people answer incorrectly. She went to the right answer. Most people just naturally think, well, it must be because the carpet's warmer and the hardwood is colder. But they're actually going to both be the same temperature. They're at equilibrium. They reach equilibrium with the air. They're the same temperature as the air. But when you put your foot on them, when you touch the hardwood, you have good contact with the hardwood over a fair amount of area. A lot of conduction can occur. And she said Nosbaz tile. Well, the worst thing would probably be if you had a nice metal floor. Because
if they can help.
yeah, they don't. You're right. But if you had a metal floor, metal's a really good conductor of heat. All metals are. And so what happens? You step on that metal floor, and heat flows into your foot. Well, it doesn't flow into your foot.
Is it getting like transferred into the metal?
Heat flows into the metal.
So
That's
then your
right.
foot's
Because your foot is hot.
Okay.
And so heat leaves your foot, and your foot feels cold. But if it goes into the metal, that metal will just transfer the heat all throughout the metal real quick. And so all that heat going into a big volume of metal, it's not going to raise the temperature much. And so you put a lot of heat in, but it stays cold. So your body is saying, I got to put more heat there because, my foot's cold and I want to warm my foot. And then the heat that comes to your foot just goes out into the metal, and you sit there and your feet feel really, really, really cold. Whereas with the wood, if you stand there for a couple minutes, it won't feel so cold because the wood doesn't conduct the heat as well. And so basically you heat up the wood under your feet, and then you'll be comfortable. What was that?
I said it, then you start walking.
Yeah, well then you're not comfortable. On the carpet, your feet are basically surrounded by air. The carpet has its little nappy things, and that basically allows your foot to be walking on air with a little bit of good insulating fiber. And so there's very little conduction that occurs with the carpet, hence you don't have heat leaving, you feel good. Because it's just, you're feeling the temperature of your foot. So that's a good example of conduction. Now, an example I like to use, this is why I fall behind in classes. You go out to the dock, and you're walking along the dock, and all of a sudden you step on a flat nail head. Not a pointy nail, but a flat nail head. And it burns. Anyone had that crazy experience?
Yes.
You're walking on the wooden dock and it was fine, and you step on that nail and it burns. Why is the nail burn you and not the wood? The nail will conduct. So the whole nail is hot, the whole wood is hot. You put your foot on, and the heat is just in the skin of the wood because it's hot, it transfers into your foot, but then there's no heat to replace it and you're good. But you step on that nail, and heat from the entire nail starts flowing into your foot and just keeps flowing because you have a lot of volume of that nail that's transferring heat into you, and it's that sustained flow of heat that's burning you.
I feel like we just stepped on one of those big sockets, almost cauterized.
Almost cauterized. Okay. Yes, this is stick a nail on ice, but same ideas. Our first and only clicker question. Oh, good. No, I did not want to install in the middle of class, just for the record. All right, so you may answer now. If you hold one end of a metal bar against a piece of ice, the end in your hand will soon become cold. Does cold flow from the ice to your hand? That's going to sound really good on the recording. Cracking my nails right next to my nails, my knuckles.
No, but now you said it, and it's incriminating.
Self-incrimination, Where's Miranda when I need him? Well, okay, Miranda was the reason that they... Okay, Stacy, Jocelyn, Carmen, Maggie, and Brittany. Carmen E. Brittany. And it's just... All right. Let's see what we got here. We had 8 that said yes, 10 that said no, and none in between. This is a perfect one to talk to your friends about. Discuss it. Make sure that you convince them that you're correct and they're wrong.
I feel like but also because I feel like it would go flow into that. What?
I don't want to change my answers. I'm supposed to do that right.
Just because.
Something like
I usually have no thought process here. I just think the answer is no.
I thought yes, but see, he was talking about the flow of the heat from stuff into the cold, so what Valerie is saying makes sense.
I feel like the metal will just take the cold. And yeah, so
Okay, you can go ahead and answer again.
I don't know. No, the cold flows from the metal, not the ice. That makes no sense, does it?
Stacy, Casey, Hannah, Jackie, Jocelyn.
I don't know.
Yeah, I don't know.
Good points, and I
When in
don't
doubt,
know.
you just know.
I don't know. Well, actually, our teacher always told us when in doubt, pick C. Because the probability of it being C is higher than the
That's
other
true.
numbers.
I think all of my potential test question answers have been C. Just in case
For some reason,
that's on the
we
quiz.
gravitate towards the third.
Okay, still missing Casey, Hannah, Jackie, and
Oh, I was supposed to
Jocelyn.
answer again.
Yes.
Sorry about that.
Now, this time we had 3 and 15. So, Jocelyn, I know you're struggling with this, but your card was pulled.
All right. Well, I am one of the 3 that chose yes
Okay.
both times. I'm not really sure, but here's what I was thinking. So I figured if you had a piece of ice, the coldness would spread through the metal and then into your hand. But I was also torn to say no because it doesn't mention the flowing of the metal part, but I'm not sure if coldness can flow.
Okay. Historically, people thought it did. They had the theory of the caloric and the frigidic. The frigidic was the flow of things to make things cold, and the caloric was the flow of stuff to make things hot. But our understanding now is that it's the flow of energy. And so heat, the flow of energy, can only flow from a region that has it to another region. So the heat always flows from hot to cold. So what's actually going on here is that we have heat, not cold, flowing from the hot thing, which in this case is your hand, into the cold thing, into the metal, and then into the ice. So it's heat flowing. And I don't know if you guys have read this, but as a physicist, of course I know about this, especially the people making up stuff like saying it was Einstein. That boy was Einstein. A teacher who's lecturing about, there's no God, and if you use, empirical scientific method, you can't see, touch, feel, hear, blah, blah, blah. So there must not be a God. And then the student goes on to say, does heat flow, heat flows from hot to cold, does cold flow from cold to hot? And apparently the teacher's not a scientist, says yes. He says, no, it doesn't. Because there's no such thing as cold. Cold is just lacking, and the person who wrote this also didn't know their physics, so they said cold means lacking heat. It doesn't mean lacking heat, it means lacking energy, right? And then talks about the same thing with light and dark. Darkness is simply the absence of light. There isn't a specific thing that's darkness. It's not having the energy. Light has a certain kind of energy. And then, of course, you might have heard how many people know what I'm referring to? And then it ends with, let's apply these same rules to your brain. If anyone ever seen it, smelt it, taste it, then there must be no brain. That's not the point today, but the point is cold means it has less energy, and you don't have a flow of cold, you have a flow of heat that can raise the energy, or if it's flowing away from something, it'll leave it cooler. So the correct answer was no here, because it's heat flowing from the hotter object, the hand, into the colder object. That's our only clicker question, so I had to make sure everyone answered. So, insulation. We have insulations in our houses. When my grandmother and grandfather, God bless their souls, they went and collected lumber from the Japanese internment camps after World War II, and they built a house out of that lumber because they gave it away free. And so they had to put insulation in the walls because you don't want to get cold. In the Central Valley, it gets down to probably 40 some years. And so they put insulation in the walls. And what they put in was newspaper, which is really, really a good plant, especially if you want the house to burn down. Right? Because it's not a good insulator in terms of, being safe. But the goal was to do something to keep heat from flowing through the walls. And if you had, let's say you were crazy and you built a house out of steel, it would get really cold inside because you have heat going right through that steel. But you know what makes a really good insulator? What doesn't allow heat to go through? We have some things listed there like wood. Air is one of your very best insulators. Heat does not go through air very well. But of course, we'll see convection in a minute. Convection is when you have an intermediary. You heat this up and then it travels and air can travel. So the newspaper was there to keep air from traveling from one side of the wall to the other, right? You have a hollow wall, you put newspaper in, air is trapped on one side, air is trapped on the other, it can't travel across, and that helps to insulate. So insulation, the goal of insulation is to stop the flow of heat. And like in most of our walls, we have spun fiberglass, which is really fun because fiberglass really is glass. It's just really thin fibers of glass. And so if you crawl in it, like you have to put, TV cables through your attic, all these little pieces of glass poke into your arm. They're little tiny things. You don't see them, but you itch like the dickens. What's the point of spun fiberglass as insulation? It traps air pockets, and the air is the actual insulator. Now, glass is a pretty good insulator, but air is better, and so the goal is to trap those air pockets. Other things you use for insulation, I have a relative who's very eco-conscious and built a house that's essentially made out of styrofoam. You have these like styrofoam walls, and then you can cut out, here's where I'm going to put a door in, here's where I'm going to put a window in. Styrofoam is polystyrene that's been blown full of tiny air bubbles. So you have lots of trapped air bubbles. It's a really good insulator. Hence why I have it in my little demonstration packet here, a styrofoam cup, because it's a really good insulator. You can put really hot chocolate in there and hold the outside and you're going to be fine until you accidentally slop it over and then the liquid comes out and touches you and scalds you. I don't know about you guys. I am a super penny pincher. And so when I leave my house and it's snowed, I look at the roof to see, is there heat getting out? Is it melting the snow? And if there's places where it's melting the snow, I grit my teeth. I don't go do anything about it. I just that's energy that I paid for to heat my house. It's going up and melting the snow. So this is showing you here, this region here, the snow is not melted, but up above it, It is. Why is it not melted in the region I circled? It's not so much that it's insulated. That's the eave. That's not over the house. And so it's separated from the house, and you have all of the heat of the house is coming up and heating it up here and melting there, but here you don't have the heat of the house coming out. And so, right, because it's just got air underneath from outside. By the way, when you have all these icicles, that's generally a bad thing. Okay.
You have to break them down before they turn the cars down.
Conduction, one last thing. Please don't go fire walking. The textbook shows that we often talk about it in physics. When I was in graduate school, thankfully it wasn't my lab students, one of my classmates' lab students, he was talking about fire walking and how it's safe to walk on fire. And then the next week the students say, yeah, we were down at the dunes and we were barbecuing and we threw out those coals and we walked across them. You were right, it was awesome. And he's like, oh, what if something had gone wrong? Because lots of things can go wrong. I'm sure, I was going to say, I don't know about you guys, but I'm sure none of you have had the same experience fire walking that I did. When I was 13 months old, I snuck out of the house, followed my dad down the street. They had the wood-burning stoves there in Sierra Leone, and I melted my feet. It's actually a really sad story because my dad heard something. He had gone to the shop. He looks out and he sees me standing in the middle of these coals, and he comes out to pick me up, and it got hot. And so I started crawling. And so, I still have scars on my wrists from where it melted. And that still hurts, so I sat down. My diaper saved my butt. But when my dad picked me up, the flesh was actually dripping off of my feet, right? It can be bad. My toes all fused together. I had to come to America and have surgery to have my toes separated. So it can be really dangerous, and obviously it's a touchy subject to me. But it can also be safe if done the right way. So what's the right way? The best way to do it is to have something like a pumice, a rock that has lots of air bubbles. You can heat that thing up so it's red hot and you can walk on it. Why? All of those air bubbles means that it's a very poor conductor. And so you're only going to get the heat from the very part you touch and not from anything else. And so you touch it, you have a small amount of heat that comes into you and it all is equilibrated. Another thing you can do is have wood that you burn, and you burn it down until you have nice, thick regions that are burned, so you have charcoal. And, all right, that's what I learned to call it anyway. And that, once again, is basically a structure with a whole bunch of air trapped in it. And so it's a very good insulator, and so it's only the heat you touch. If you still have a flame in there, oh, that's really bad. And so every now and then you have these really stupid conferences where people come, they're getting self-confidence, and they walk through the fire. And every now and then they don't prepare it right, and people suffer major injuries because they were showing they had confidence.
Why can't you just walk across lightning?
That is another way of causing pain, but the goal is not to cause pain. There are some other things that also make it safer to walk on coals, like if you have moist grass and you get the bottoms of your feet wet, water will absorb a lot of heat compared to other things and not change temperature much. So that water will help to keep your feet from getting overly hot. That's why in the Central Valley of California, they will, when it gets down to freezing, they will water crops because the water will freeze and not change temperature much, so you're less likely to freeze your plants. That and those smudge pots, right? Do they still use those?
I don't know.
Smudge pots, they basically put motor oil in these things in the field and light it on fire and keeps the field warmer. It's not environmentally friendly. Okay, the second one, convection. Convection is the flow of energy through an intermediary, through a fluid of some sort. So a standard convection is what you see, and now I will go ahead and light my fire. Oh my goodness. I'm going to have to retire this hose. Let's pray that nothing blows up, eh? That's a good prayer. It's leaking right there. Yeah, this is not good. Okay, well, it'll be okay. So we have the flame. Why does the flame go up?
Heat rises.
Because heat rises. Why does heat rise though?
Is it less dense?
If I put my hand up here, it gets really hot, right? If I put my hand over here, does it warm up? It does a little. That's the last one. I'm turning it off because it really is stupid to know that I'm leaking gas and keep the flame going. I'm tired of that hose. Convection is what causes people to say heat rises. Heat rises is technically not accurate. It is practically correct, but technically not accurate. What happens is air comes in, gets warmed up by the combustion, and then the hot air, because it's moving faster, it pushes off things harder and it expands. But if it expands, it's less dense. And then that less dense air floats up. So it's hot air that rises because it floats. It's not technically heat rises, it's hot air that rises. But that's the essence of what convection is. So you can have something like a convection oven where you heat up air over here, a forced convection oven. You heat it, you have a fan that blows the air over to your food, and then cooks your food by blowing the air over there to heat it. Convection is really important to us because things like our weather cycles run on convection. The Earth has an equator, and the equator tends to be warm. And because it's warm, the air gets heated, and that hot air rises. So you have air that rises at the equator. Now, as it rises, it expands because the pressure is less. But as it expands, expansion is a cooling process, so it cools. When it cools, it holds less moisture. And so that hot air rising often causes water to fall out. So you have lots of rainstorms. When I was living there in Africa, it was pretty tropical. And we had the wet season and the dry season. Lots of rainstorms, less rainstorms. Then it gets up here and it separates in the high altitude. And then it comes down. When it comes down, it gets compressed, it gets hot again. But it had dropped out its moisture when it went up. So now you have hot, dry air coming down. Doesn't rain when you have hot, dry air, right? And so that tends to make deserts. The hot, dry air comes down around 30-ish degrees north and south. And so it tends to make your deserts in the region where it comes down. And our weather patterns are largely dominated by this effect. Pictures to illustrate. Water, if you live by the ocean, during the daytime, the ground warms up more than the water. And so hot air rises, goes over the water and sinks. During the nighttime, the ground cools more, the water stays about the same, so now it reverses. And so that's why you have the morning and evening breezes if you're next to a large body of water like the Pacific Ocean. The final way of energy transfer is radiation. Radiation is actually waves, electromagnetic waves. The same thing as light. Light is a form of radiation. And if things are hot enough, they give off light we can see. And so that's how an incandescent light bulb, like the light that's in the projector here, or if you have the typical light bulb that you grew up with, those are pieces of wire that you make really hot, and that's why they're giving off light. And that's radiation. So, the wavelength is the length between repeating of a wave. So if you watch an ocean wave and you have here's one and then 20 feet later here's another rise, the wavelength is the separation between those. Cool energy has a long wavelength, long range between the peaks. As it gets hotter, that distance gets shorter and shorter. And so frequency is how many times per second it comes. The frequency for the peak in the radiation is proportional to temperature. You make an object hotter, the frequency where it has its peak radiation gets higher. And we're out of time.
Can you go back to the first line of radiation? Yeah, thanks.
Have a good day.